Alright, so we actually don't have a ton of notes to do, but I felt like yesterday I talked a ton and actually made like this many points. And I'm like, that was really verbose way to say something very, very small. So sorry if I said it a million times and it seemed boring, but because it's such a big concept, I feel like it's so important to make sure that it's really clear. What's that? No, yesterday. Were you here yesterday?
Yes, I was. I watched the video for Monday's class.
Gotcha. Okay, so yesterday what I was trying to explain was when you take a derivative and you get critical values, whether it's from the derivative being 0 or undefined, those critical values can give you maxes and mins. And to tell which one's a max and which one's a min, you look and see if the derivative goes from positive to negative, in which case it's a max, or negative to positive, in which case it's min.
So that's all we have to do yesterday.
I could have said it in 5 minutes, but it was important to go through the deal.
She explained so much.
That was yesterday.
I explained. Wait, what?
That was yesterday. We just
That was yesterday.
She did like a mini recap.
So,
Yeah,
Like taboo that entire time.
we could have. But I think it was important to like reiterate all the other stuff. But the thing that I didn't really say until we were doing an example was not only if the derivative changes from positive to negative, you have a max, or negative to positive, you min, but if the first derivative is positive, what that means about the function. And I kind of said it yesterday, but then I just glossed over it. Yeah, we didn't really make this clear. Did I make it clear?
It was on a test, and I'm pretty sure we had to know it.
Well, anyway, that if the first derivative is positive, that means that the function itself is increasing.
Oh, yeah.
Oh, yeah.
Did we learn that?
Maybe you did. I don't know. Okay.
Yeah, you gave
That
us
was-
the graph
that was on the
of
test.
a function, and we had to find the graph of the derivative. Same
Value this information.
Classy. Testing us on stuff you haven't taught yet.
I guess I did. So I guess we did talk about
Remember,
it.
she
Okay.
taught it.
Fine. Fine.
Underestimate.
We just learned the whole concept in 2 minutes.
No, that's not what I was going to say. Okay. So the second thing we got to talk about. So we have covered now maxes and mins, and we've covered when functions are increasing and decreasing. But what we haven't covered is this. You can have a function increasing and look like that. You can also have functions increasing and look like that. And they're very different. And the difference is its concavity. This function is concave down because it looks like a frown. If something is concave down, it looks like a frown.
Is that where you were going? You should have put like a happy thing.
Not really. I was just being weird. And this is concave up.
Thanks.
And it looks like a cup. Wow.
That's good. That one's good.
Well, if I did the whole thing.
It's a crack.
Okay, if I continue.
It looks
There
like
we
a
go.
bowl, okay?
Does bowl rhyme with concave up?
Does anyone have lead?
Yes.
Definitely.
No.
So,
Does cup rhyme with concave?
rhymes with up.
What's your point?
So how do I what am I writing
So
down
I'm
for this?
nothing
In my
yet.
notes?
I'm just.
What about convex?
Oh my god.
I don't get it. But what's it
What's convex?
The other way.
The other way.
What's the other way?
Well, the frown should be convex and the cup should be concave.
The concave down part can go the other direction too.
Yeah, that's convex.
What I was trying to say is, no, so this is called concave down all the way, both
It could
sides.
be either one.
Oh my gosh.
That's how you're looking at it.
Yeah, I know, it's on perspective.
If I have a function that is increasing, it could
Concavity is
look
in the eye of the
either
beholder.
way. I could also have, so if function's increasing, it could be increasing and concave down, or it could be increasing and concave up. I could also have a function that's decreasing, and it could be concave up, or it could be concave down and be decreasing. So this one is concave up, because it's making part of a cup. And this could be concave down, and it's making part of a frown. So the question is, we need further tests, because if something's increasing, and I'm supposed to draw it, How do I know if I'm supposed to draw it with this kind of curve or this kind of curve? It has
Second
to do with the
derivative?
slope of the slope.
Ooh, double derivative.
Second
So it
derivative.
has to do with the second derivative. If something is concave down, the second derivative is going to be negative. Because it's kind of like saying the rate of change of the rate of change is getting less. Because if something is concave, if my second derivative is negative, I'm saying that the rate of change, that the rate of change of the function is decreasing. Well, that makes sense. If I have something concave down, it has a bigger slope here. As I continue, the slopes get smaller. So the rate of change of the rate of change is negative. The rate of change is getting less. So this has a second derivative that's concave down, and so does this. I mean, a second derivative that's negative, and so does this. So if something is concave down, the second derivative will be negative. And if something is concave up, the second derivative will be positive. Okay, we said that when a function's derivative goes from positive to negative, the first derivative goes from positive to negative, we get a max. Negative to positive, we get a min. When the second derivative changes from positive to negative or negative to positive, it looks like this. Like, let's say I have an increasing function the whole time, and let's say at this x value, my concavity goes from concave down to concave up. It would look like this. This part is concave down. This part is concave up. And at the place where it changes from being kind of, rounded like a frown to rounded like a cup is called a point of inflection. And what do you think is true at that point of inflection?
It's inflected.
Yay! The second derivative, because it's concavity, equals 0.
So is that graph already a derivative?
No, this is some function f. And the function, so if this is f, if this is x, f of x, if it's always increasing, what does that mean about its derivative? Always positive. So this function that I drew, whatever random function, has a derivative that's always positive because it's always increasing.
Oh, wait. So the second derivatives?
When its second derivative changes from positive to negative, or vice versa, it gets a point of inflection. And it's just where it changes from looking like a cup to a frown, or vice versa.
So this is the graph of the derivative.
This is still the graph of f. Let's do an example that's going to make some more sense.
X cubed.
Yeah, let's do x to the third so it makes some sense.
Wait, but Matt just asked if the first derivative equals 0 also. If
Yeah, the first derivative would be 0 also. So that's what we talked about. The first derivative being 0 doesn't guarantee it's a max or a min. It just guarantees, it doesn't guarantee anything. Something's going to happen.
But if its second derivative is 0, then it's a point of inflection.
Yes. Only if the concavity changes from one side of it to the other.
Okay. So
Is that really 0? Isn't it always positive? The first derivative on that?
The first derivative is always positive.
Yeah, even at that point of inflection.
Double derivative.
The first derivative.
No, it depends. Let's do, no, because if it's x to the third, the derivative is still going to be 0 at 0. So I guess it flattens out. So let's make this more concrete and let's look at x to the third. So we all know what x to the third looks like. Okay, and it looks a lot like what I just drew. But let's just do it so that we see it algebraically or calculusly. So the first thing I would do is I would take the first derivative, and what am I going to get? 3x squared. I'm going to find the critical value, so I'm going to set this equal to 0, and what would x equal? 0. If I didn't already know what this graph looks like, I would make a number line out of that, and I'm going to make it anyway just to like prove the point. If I plug a number in to the first derivative that's less than 0, so like -1, do I get a positive or negative result? Positive, right? Because I'm squaring -1, so I get a positive result. And if I plug in something to the right of 0, like 3, I still get a positive result. What that means about f is that f is going to be increasing always and have nothing special at 0 that we know about yet.
It looks like a face.
Alright, so far we know f is increasing always. It makes sense because its derivative is 3x squared. Whatever I plug in is going to be a positive, give it a positive derivative. It's always increasing, and nothing really special happened here other than the derivative is still 0 there. So this should be flattened out. Okay, if I want to draw it a little more dramatically, this kind of tells us that this graph actually does have a horizontal tangent line at 0. Okay, usually we don't draw it so flat there in the middle, but apparently it does. Okay, now look at the second derivative. Second derivative is 6x. I set it equal to 0, and I get the same 0. Make a number line out of it. And now I'm going to label the second number line with the second derivative information. So now when I plug in something negative, or less than 0, I get a negative number, and something bigger than 0 gives me a positive number. That tells me that f is concave down on this interval and concave up on this interval. And that this point is special. 0 wasn't special for the first derivative, so I didn't label it at all. Nothing changed around 0 for the first derivative. It didn't go from positive to negative or vice versa, so there's no max or min. Now that this changes, this is called a point of inflection.
Wait, why?
So it's specifically called a point of inflection because the concavity changes. Points of inflection only happen when concavity changes, not when the second derivative is 0, but when the concavity changes. Because I could have a second derivative equals 0 and have the concavity not change, but here it does, yeah.
When concavity changes for the original graph.
Yeah, so all these number lines, like this, these are the qualities of f. These are the qualities of f,
Oh, okay.
okay?
Does the second derivative have to be 0?
For it to be a point of inflection? Yeah.
So like that's how you know if you like couldn't draw it. Like you know how to draw y equals x. Like but
What's the relevance
if
of that?
we got something that we couldn't graph,
Then we would use all this stuff. We're going to do it in a minute. So what's the relevance?
Yeah.
We're going to graph some crazy stuff. This is just to show how it works. So we're going to graph some crazy stuff you wouldn't be able to graph otherwise. Okay? Okay, excited?
Not really.
No.
Yes.
Alright, wait, I have another question.
Yep.
Does the first derivative have to be 0?
And for a point of inflection? No.
Wait, Zach, are you taking?
Yes.
Can I say something? I watched the video on Monday, and I didn't see any of the examples.
So,
Just thought I'd point that out.
Did you see any gym?
What?
Did you see any gym?
I did see some
Okay.
gym.
You guys
There
do
was gym, but there was no
show your new
graphic.
cast.
Because there was lots of graphics.
Show it off, Jim.
He just left the camera there, didn't even look through it.
I'm going to give it back to Eric, aren't I?
You finished today.
We finished today. Okay, so let's do one. Let's see what we want to do. Let's do... That's really hard.
Let's do it.
All you really need is Jim. I mean, how much do you care about examples?
I don't care that much. Just kidding. Okay, here we go. I just want to pick a good one. That's boring.
What is that?
Okay, ready? Or you're gonna hate this. Too bad.
Oh, I hate it already.
one that's like going to be really arithmetically bad, arithmetically annoying, and then we'll do one that's not quite so annoying.
Which one's what?
This is the annoying one.
Wait, what am I doing?
Am I trying to grab this?
So the question is,
Yep.
find all maxes and mins, find all points of inflection, figure out the qualities of f, and graph it. Now, use all the information in your arsenal of information. For example, is this function even or odd?
Even.
It's even. Okay, pick up on that. You've got all even powers, so like it should be a reflection around the y-axis. It's to the fourth, and it's a polynomial, so like, how is it opening? Both ends are going up, so we know that for sure. In the middle, it could. How many zeros could it potentially have? 4. So just kind of keep that in mind that this is what we're looking at. We could have 4 zeros. It's going up. The two ends. What's that?
And it has a y-intercept of 1.
It has a y-intercept of 1. What else was I going to say? Does it have any asymptotes or anything?
No.
No. Does it have any place where the derivative is going to be undefined?
Well, kinda.
No.
Think about it. If you know what you know it's a polynomial, is there any place where it's going to have corners or cusps or no?
No.
Okay, so it's going to be nice and defined. It's just going to be gross. You want to start on the math yourself, and then we'll go through it. So take your first derivative. Yeah, I know, Dee. Sometimes people like to combine it and do both the tests on one number line. I don't know which way is easier. I like to do it all in one sometimes, but I'm afraid that's going to be too confusing to start off with.
Wow, that is annoying. Because now I have to test in between 1 and 0.
1/2.
Arrgh. But I hate working with lines.
So something less than -1, like -2, is going to give me a negative times a positive. Something in between, like -1/2, is going to give me a negative and a negative, right? And if it's even, shouldn't I get the same thing? But, no, not so.
Because this
Yeah.
thing's odd,
Yeah.
so you should get the opposite.
Well, because like if it goes like this, yeah, it's not going to be that. So 1/2 is negative.
But because the derivative is odd, it should also be the opposite.
Right. Did you have fun today?
No.
Did you have fun?
Yeah, it was good.
That's good. None of your business.
Identify yourself.
Okay, so I mentioned yesterday that this number line is enough of an explanation on the AP test of what you're being asked to justify, as long as you label it. If you don't label the number line, then they're not going to take it as an explanation. You've got to put y prime with your pluses and minuses, meaning this is the sign of the derivative. And you've got to put regular y, or regular f of x here, with explanations of what those negatives and positives mean. If it doesn't look exactly like that, it doesn't count as justifying your answer.
What if it should be first?
Upside down's fine. It's just got to have all that stuff on it. So then I go through and I'm like, all right, if I went from a negative to a positive derivative, what's happening at -1? If I go from negative derivative to positive derivative, I've got a min. If I go from a positive derivative to a negative derivative, I've got a max. And from negative to positive, I've got a min. find all these ordered pairs now, because I'm going to have to put them all into the graph anyway. So if I'm going to find the ordered pair, do I plug -1 into the derivative or the original?
Original.
Oh, original. So plug -1 in, and I already did these problems, so the math is really annoying. This would be -1, -1. This one's easy, and 1 negative. Okay, did you get all that so far? Okay, now I go back, and I take the second derivative. Use your brains, and don't use this one to take a second derivative. There's no point in using the factored one. It's more complicated because you need product rule. So go back and take the second derivative from there, and we're going to get 24x squared minus 8. And x is going to be positive or negative square root of 1/3. That's where it gets really tedious.
So positive, negative, 1, 9.
No, that's the wrong way.
Oh, 1/3.
Yeah.
No.
So we make another number line. And is the square root of 1/3 bigger than -1? Is it, or bigger than 1 or less than 1?
Bigger.
Less than 1, right? So it's going to be between -1 and 0. So I'm going to make a number line that kind of has this matching up as far as position of numbers, so I know what to do when I'm graphing it.
Why double prime?
Oh, thanks. Alright, so pick a number less than -1, and I'm going to get a positive number. Pick 0, and I get a negative. Pick something bigger, and I get a positive. So this means that y is concave up. Oops. Concave down. And concave up. Got all that? Alright, again, I'm probably going to say this again because I know people mess it up. You only have a point of inflection when concavity changes. So just keep that in mind, that just because my second derivative is 0 does not make it a point of inflection. What makes it a point of inflection is the concavity changed. So this is a point of inflection, and so is this. This one is at negative that, and I had to do it on the calculator, negative 0.111. Negative 0.111. Let's graph this bad boy. When I'm graphing, I want to put down all the points that I have first, and then I just connect them in the way that I'm supposed to. So I've got a point at -1, -1. I've got a point at 0, 1, and a point at 1, -1. And then negative root of 1/3, negative 0.111, and over here.
This is disgusting.
How do we know it's a cusp, not a cusp?
Never a cusp.
It's never, because the derivative would have to have been undefined. For there to be a cusp or something, the first derivative would have been undefined somewhere, and it's not. So we don't ever have cusps for this one. We don't have corners, and we don't have asymptotes because the derivative was never undefined. The derivative was only 0. Like when we took the derivative, it was equal to 0. We never had to worry about where its denominator was 0, so we never had to worry about where it was undefined. Alright, and we just go for it. So to the left of -1, the thing is decreasing and concave up. So from -infinity to -1, oops, it's decreasing, and it looks like a cup. Well, at -1, -1, this is supposed to be a min. So then I'm going to switch directions. I'm going to go over to being increasing, but I'm still concave up. Okay, so as I go from -1 to my next x value, I'm still concave up. I still look like a cup. From negative root of 1/3 to 0, I'm still increasing, but I have a point of inflection now, so now I'm concave down. So from this spot, I'm still increasing, but now I've changed direction, kind of. My curve has changed direction in a way. From here, at 0, I switched to decreasing, and at 0, I had a max. So I'm going to start going down, but I'm still concave down, so my loop still stays nice and smooth. At the square root of 1/3, I have a point of inflection, my concavity changes, but I still keep decreasing. So I move this way, and then past 1, I'm concave up, and I'm increasing now.
You care about where the zeros are?
No, no. You could find them, it's not that big of a deal. You'd have to find a really good calculator for this, which kind of defeats the purpose.
You could just use
Q over Q factoring.
quadratic.
No, because
Oh,
it comes
sure.
out to something nasty. I already tried it. It comes out to like 2 plus or minus root 2 over 2, just for the squared part, and then you have to work from there.
Yeah, it's fine.
So it's really disgusting.
Did you get it?
Yeah.
Let's do another.
Yeah. I wouldn't want to factor that.
Alright, let's do.
So yeah, you'd have to go to your calculator eventually.
Unless you want to take the quadratic formula with that inside.
Okay. Take this. I'm not sure which problems are going to pick you up, but I'll put them in the keyboard list.
No, you just have to take the square root of that. Yes,
Yeah. At some point you would.
There's a problem.
it's already gone through the quadratic formula, so you don't need to put it again. You just take the square root of that.
This is awesome.
I guess so.
Okay.
How nasty is it?
It's still pretty nasty.
Yeah, these take a lot of space. A lot of space.
This is annoying.
Okay, yeah, start it. Oh, come on.
Product rule for the whole year. Product rule.
This is disgusting.
You know what? Don't judge it, okay? Did it ever judge you? Exactly. Except for that stupid color Jimbo picked for his cats. Just kidding. Okay, so you might need a little help with the
Why are we doing this?
posture of this.
Why is it negative?
The other one was the hard one.
Oh, it is.
No, I think I can do it actually.
Okay. You should be able to. It's not that bad.
Oh my gosh, I think I remember this one. Like that probably.
You're thinking of when you multiplied by e to the second or whatever, and it like
Wait, don't you have to
Yeah,
set the top and the bottom to 0?
you do. what I would do, I would pull out an e to the 1 over x. And then I'd be left with negative 1 over x plus 1. Okay, I mean, let's like work through it together so that you don't make a mistake or get too far along in the wrong direction. I took the derivative with product rule. I simplified it a little bit. And then I've got e to the 1 over x. I'm going to take that out to the front for 2 reasons. I want to just see what I have. And I'll simplify this in a second. E to the 1 over x, can that ever be 0?
No.
No, it can't ever be 0. So that part's never going to be 0, but I'll get back to that in a second. I also need to worry about this. And you remember what I said about when we set this equal to 0? I think it's important, I know it's important to make a common denominator out of it. And to give myself this. Because without that, you end up almost just setting it equal to 0 and missing one of the critical values. This thing has critical values at x equals 1 for the top of that fraction and 0 because of the bottom of that fraction. And if you don't make that common denominator fraction, I think you're going to miss one of them. Because if you just, like if you said, well, this is never going to be 0, and then you set this equal to 0.
Undefined since there's the
I know.
fraction in the
Technically, this is going to be undefined when x is 0, so there actually is a critical value that comes from this, from the denominator of the exponent having a 0. So you do actually get that critical value, that undefined critical value from this, from the denominator of that fraction being 0. But if you do this, you'll also get it that way, so at least you'll, I don't know, you have a second chance to kind of get it right for yourself, even if you miss it. Yeah.
If we have that situation, but what if we don't have the other situation where we have an x over x?
Then you're going to have to pick it out from here.
So how do we know how to do that?
Just that, look, you've got a fraction that has an x in the bottom, it can't be 0. I've got a fraction with x in the bottom, and that fraction can't be undefined, so x equaling 0 has to be a critical value. Because if x is 0 just for this part, it's going to make this undefined. Okay? So,
We ignore the undefined.
we don't ignore the
You
undefined.
have to know them.
Yeah, because it could be a corner or a cusp, or it could be where the function itself is undefined. Look back at the original function. That function itself is undefined at 0, because when I plug 0 in, that fractional exponent is 0. Yeah. So we get to make a number line with 0 and 1.
Wait, so which one was overridden? The 0
The
multiplier?
0 from the original is going to override anything else.
I mean, the 0 multiplier or the undefined?
They're both what makes it undefined anyway.
I mean, in the original problem, like, you had 0 times.
Oh, I see what you're saying. I think the undefined, but when you see what this looks like, it almost has both. It's a little weird. Yeah. Okay, so we plug stuff in to the derivative. Stuff less than 0. Again, if I'm looking at the derivative and I look back at my factored version, is e to the 1 over x ever going to be negative? No. E to the 1 over x is always going to be positive. It could be a fraction, but it's always going to be positive. So all I have to worry about is this. So if I plug in a number less than 0, like negative 1, am I going to have a positive or negative number? Oh gosh. So if I plug negative 1 into here, I'm going to have a positive. If I plug 1/2 into here, negative or positive?
The second derivative is disgusting.
Negative.
1/2 negative plus 1 is negative. And then like 2, I get something positive. So y is going to be increasing, decreasing, and increasing. It's going to have a max here at 0, comma, I don't know. And because if I plug 0 into there, I don't really know. We'll get to that. And I'm going to have a min
What's this test?
here at e.
Isn't it undefined?
Yes, F1?
That's my question. No, it's 0.
Well, like,
Slightly. Somehow.
So
Sometimes.
is
Well, if I plug in 0, it's kind of like
Times an
Zero.
undefined
it's 0
equals-
times something that's undefined. I'm thinking the undefined is going to overrule it.
I'm just gonna put 0 times.
But then, so with any problem, you first find the zeros, and if you see there are underlines, you ignore them until you get to this issue. I'm so lost right now.
If I see zeros from the original,
Because like, okay, if you look at a regular function, I can see that it's x, then look, the derivative of the function, right?
yeah.
And if you see that they're undefined, you know that those are critical values, because you see that if x is 0, that it's undefined. What do you do with
Put it in a number line.
But what if it's not 0? But what if it's not 0? What if it's like,
Undefined in the original,
yeah.
just put it in the number line anyway.
Put everything in the number.
Everything you find from the first derivative being undefined or 0, put in the number line. Because it could be a potential change. And it is a change.
Okay, go on.
Okay.
What if you get x equals undefined?
So where is the max?
Like, if, well, you know how you set every x and every x in the equation to either 0 or undefined?
Right.
To get the critical value.
Right.
What if you get x equals undefined?
You wouldn't.
You'd have a specific place where x is undefined.
I'm not gonna do that. I'm just
You
not
wouldn't
gonna
be
do
setting
that.
You
x
wouldn't-
equals
yeah.
undefined, you'd be setting the denominator that's
Oh, to 0 and then it would.
So much to
Oh,
talk
God.
about.
Okay,
Cool.
I'm good.
Okay.
So where's the
We're gonna run out of time.
Can we just
Thank
grab
God.
the values and plot it?
Can we just put it in our calculator?
Son, this is what I got for the second derivative.
The calculator
don't
doesn't-
even-
actually.
I got
I'm
negative
just
e
gonna
to the 1
continue
over
and
x
try to
over x
finish it.
squared plus e to the 1 over x over x minus e to the 1 over x over x squared. That's you're never gonna figure that out for a
I'm gonna
constant
pause it for
function.
tomorrow. Because you don't have time to finish it. We still have too much left.
You ready to make
But we are finishing it tomorrow.
Jen, this second derivative is nuts.
It's not that bad.
It's that bad.
yeah, that.
It's really annoying.
Finish it tomorrow.
What are we doing on Friday?
I still don't know. More of this.